Thank you very much for coming out here. As Michael said, my name is Paul Lasky, and together with Thrane, I'm going to tell you about this really exciting new discovery that we have of gravitational waves coming from a binary neutron star system. And this is something that just happened a few months ago, and we've been working very, very hard in the intervening period to bring you some of the science that we're going to talk about today. So the way this is going to work, I'm going to tell you all about what gravitational waves are and bring you up to the period of about the middle of August of this year. And then my colleague Thrane is going to take over, and he's going to tell us all about the actual exciting discovery. And then at the end we'll have a panel session. We'll get a whole bunch of our group to come down and answer any questions that you might have associated with gravitational waves or with binary neutron stars in general. Okay, so let's get started. I'm going to take you the whole way back to 1915, and hopefully you recognise this guy up here, Albert Einstein, and in 1915 he told us how gravity works. So there was a period before that where Isaac Newton believed we knew how gravity worked from Isaac Newton's theory of gravity, but it turns out that that's all very wrong, and what they teach you in high schools is not quite right. So Einstein made many amazing contributions, and I don't normally like putting equations in public talks, but I'm going to do it anyway. So what you can see here, we've got this one equation which is now known as Einstein's field equations, and it looks quite simple, and in fact it is actually beautifully simple, but underneath there's a lot of really complicated mathematics which I'm not going to take you through. But I do want to point out a couple of important features that's going to help us understand what gravitational waves are. So you can see this equation. On the left-hand side we have this big G with these two subscripts, mu, nu, Greek letters. And what this represents is space-time geometry. And Einstein told us, in fact, that gravity is not actually due to forces between any two objects, but it's actually due to the curvature of what we call space-time. And this is this four-dimensional space-time, which I'll talk about in just a second. But on the right-hand side, we have 8 pi. These are just numbers. You know that pi is 3.141 blah blah blah. So this just a number, and it's multiplied by this t with an underscore mu nu. And what this represents is all of matter and all of energy. And so the classic analogy that we think of is depicted here in this little diagram, where we have an Earth and it's sitting on some grid. And the way we think about this is you can imagine putting a heavy object like a bowling ball on top of a trampoline. And what happens is when I have this bowling ball sitting on a trampoline, just like the Earth sitting on this grid, the bowling ball acts to bend the surface of the trampoline. And this is the way gravity works. So you can now imagine if I put another little ball somewhere on this grid, then it's going to want to move towards the Earth. In other words, it's going to feel this gravitational attraction towards the Earth. And this is actually the way we think about gravity. And in fact, I could do another little experiment here, and I could put another ball in, and I could send it on an orbit. And if there was no friction or anything in this space-time, then on this orbit, you could see it would just go around this Earth, and it would just orbit around it. Okay? And this is the way we think of things like the moon orbiting the Earth, or the Earth orbiting the sun. And this is a beautiful depiction. This was beautifully summarized by John Wheeler, when he actually said space-time tells matter how to move, and matter tells space-time how to curve. And this is really now the way that we think about gravity. So you can take this analogy one step further, okay? And now imagine I have this object that's moving on the surface of the trampoline, and as it moves across the surface of the trampoline, if you look really, really closely, what you'll actually see is, because of the friction associated with the contact between the trampoline and the ball, you're going to get little ripples of curvature on the surface of your trampoline that emanate outwards. Just like when a duck swims along the surface of a pond and little ripples of water emanate outwards from the surface, from behind the duck. And this is really how we think of gravitational waves. So gravitational waves now, if I have any mass that's moving in my curved space-time, then it creates these ripples in space-time. And you can see I've got this little animated GIF where I have two masses and they're moving around each other. And they're moving around each other right at the center here. And as they move around, you can see that the space-time, the curvature of the space-time is rippling, and those ripples are traveling outwards. And it turns out from Einstein's theory, we can predict that those ripples should travel at the speed of light. And not only should they travel at the speed of light, but they should carry actually any energy and angular momentum. Okay, but this is a reasonably abstract concept. And so I need to then ask the question, well, suppose I have these gravitational waves being created, I have these ripples in space-time being created. What does it actually do to some body, some physical entity that's just sitting in space? Now, I'm a theoretical physicist, so what I'm allowed to do is I'm allowed to take a ring of test particles, which I've got shown here, and I can take this ring of test particles and I can just put them out in space. Okay? So I'm going to do that. This is a thought experiment. I'm going to put a ring of test particles and they're just going to sit out in space. They create a circle, so each particle is the same distance away from the particle on its opposite side. And then no gravitational wave is passing through. These things are just going to sit there happily and do nothing. What happens when a gravitational wave passes through? And what I'm going to do is I'm going to pass a gravitational wave into the screen now. As a gravitational wave passes through, you can see this starts to, there we go, this starts to actually move. And it's actually the physical distance between any two particles is actually changing. And it's doing so in a very characteristic way. So what you can see here is that at one period, for example here, you can see it's getting, this ring of test particles is getting stretched in one direction and squeezed in the opposite direction. And then some period later, it's getting stretched in that opposite direction and squeezed in the first direction. So in other words, as a gravitational wave passes through me, at some point I get made slightly taller and slightly skinnier, which is great. I need all the height that I can get. But at some time later, I get actually squished, so I become fractionally shorter as well as slightly wider, which is not so good, okay? And so this is actually the way gravitational works. But you can ask the question, well, how can I go and detect something like this? And we went to Michael Morgan, our head of school, and we said, we want to build a gravitational wave detector. And he said, how much money do you need? And we said, we just need $500 million. And he said, go away, build it with some Lego. So we did. So we built our little gravitational wave observatory just using some Lego. And here it is. So this is a really good schematic to show you how a gravitational wave detector actually works. And I'll walk you through it briefly. So what you can see down here, we have this laser that's input, and it's a very high-powered laser, and the laser light comes in through a cavity here, and it hits this mirror that you can see, this white Lego blocks that are on an angle. And it hits that mirror, and half of the laser light is going to go up this cavity in the vertical direction on the page, and the other half of the laser light is going to come horizontally in this direction here. So the light that travels vertically is going to go up. It's going to hit a mirror up the top, and these are beautifully pristine mirrors. They weigh 40 kilograms each. It's going to hit this mirror, and then it's going to come the whole way back down. This is actually a vacuum tunnel. It's going to come back down this vacuum tunnel until it hits this half-slivered mirror again. Likewise, the light that goes along the horizontal direction is going to come out, hit another one of these mirrors at this end test station here, and then come back until it hits this first mirror where it got split up. And so what you can see is if these two arms are the same length, then the two light beams will travel. It will take them the same amount of time to travel through each arm. And so when they recombine at this mirror here and come out to this blue Lego block, which is a photodetector, photodiode, and you can see when the light recombines there, it's going to do so in such a way that says, aha, these two arm lengths are exactly the same. So you can ask the question, what happens when a gravitational wave passes through? And when a gravitational wave passes through, this is what happens to my detector. The physical length of the arms changes. And because of this stretching and squeezing of space-time, the physical length of the arm changes in such a way that at one period, this vertical arm gets longer, and at the same time that that gets longer, the horizontal arm gets shorter. And then half a period later, half a cycle later, the opposite is true. And my arm on the vertical direction is shrinking, my arm in the horizontal direction is increasing. which means that I get this differential change in arm length between those two arms. And so when my light travels down one arm, comes back and recombines with the light that's come through the other arm, you can actually detect that there was a change in the differential arm length of this detector. So this is absolutely fantastic. This is the way a gravitational wave detector works. But aha, I hear you saying, Paul, this looks like an incredibly large effect. Why has it taken us so long to detect these gravitational waves? And clearly, because Michael wouldn't throw up the $500 million, clearly the effect is not this big. So instead of building LEGO detectors or LEGO LIGO detectors that are sort of 10 centimeters across, we build them much bigger than that. So here is an actual image, almost, an actual image of the LIGO Hanford Observatory. And what we've done, just to show you and to give you a sense of scale, is we've put Ayers Rock in the center here, okay? So this is obviously a fudged image, but we've put Ayers Rock in to show you that these arms that we were talking about on the previous slide are actually 4 kilometers long. So here we have this control station. This is where that laser light gets generated. It gets put into the mirror and half the laser light comes out along this direction. The other half of the laser light comes along this direction. These are 4 kilometer long vacuum tunnels, some of the best vacuums in the world. They hit these mirrors, which are right at the end. You can just sort of make out the end stations. They hit these mirrors, the light bounces back along the vacuum tunnel and recombines at that control station. So it travels a total distance of 8 kilometers, but in truth it actually travels a lot more than that because we bounce the light backwards and forwards a number of times to increase the effective length of these interferometers. So this is what the actual interferometer looks like. And what I'm going to show you now is actually a movie of how we create these gravitational waves. And what this movie is this is a movie of the first gravitational wave detection that was ever made. So what you can see here, we have two black holes. This is a computer simulation where we're actually solving Einstein's field equations. And we have two black holes and they're orbiting around one another. And as they orbit around one another, they're actually getting closer and closer to each other. And the reason they're getting closer and closer is because they're losing energy from the system to these gravitational waves. And what we're depicting down here, if you can see it, is we're depicting the gravitational wave signal that is coming to our detector as these two black holes merge closer and closer to each other. So they get faster and faster and faster. The amplitude of the signal grows, it gets louder and louder. We're slowing the movie right down now so you can see what's happening. You can see this curvature of the space-time in the colors. You can see these ripples going out. Now we've frozen the movie because at this point those two black holes have actually collided in the sense that the two event horizons have touched and we just form one black hole. And actually the movie is kind of anticlimactic in the sense that we now just have this one black hole sitting there. You can see these gravitational wave ripples emanating away at the speed of light, and then we have the credits. And this was what was first detected back in 2015 with an event that we now know as GW 150914. And this is it. This is what was detected in our gravitational wave observatory on the 14th of September in 2015. So what I'm showing here is two plots. And on the left-hand plot, this is the actual data that we received in the Hanford detector in Washington in the northwest of the USA. And what you can see is we have this very characteristic signal. So it oscillates. As it oscillates, the signal gets louder, gets bigger, but as well, the peaks between any two the distance between any two peaks actually gets closer and closer together. And the reason those peaks get closer and closer together is because the two black holes that are creating these gravitational waves are coming closer to one another and traveling faster and faster. And then all of a sudden you get this big sort of peak at in the last couple of cycles, and then the signal really just switches off. And the signal switches off because these two black holes have just formed one black hole. That one black hole very quickly rings down. It emits any asphericity that it has, and it just becomes this one rotating black hole that's just sitting out there in space, not emitting any gravitational waves. Now, had we just seen what was in this left-hand plot, we would have been a little bit excited, but we wouldn't have had any real way of saying, this isn't just some noise in our detector due to maybe seismic activity on the Earth somewhere, or a truck driving by and a nearby road, or something along those lines. So what you do is you build two detectors. And the second detector is 1,000 kilometres away. It's in Louisiana in a little town called Livingston. I was just there actually last week. It's an odd little town, but a beautiful location. And so you build this other detector 1,000 kilometres away. And what you can see on the right-hand side in blue is the data that we got from the Livingston Observatory. And overlaid on that in red is the data from the Hanford Observatory. And what you can actually see is the data lines up absolutely beautifully. So we detected this same signal in our two detectors 1,000 kilometres away. And the signal was separated by less than 10 milliseconds, which is the amount of time it takes for either a light wave or a gravitational wave to travel from one detector to the other. So of course, had a truck caused the signal in Hanford to look like that, then there is no possibility that that same truck could cause the same signal in a detector 1,000 kilometres away. So we know that these signals had to be of astrophysical origin. Now, there are a bunch of numbers on these plots. One thing you can see here, and this will become important later, is that the signal just lasts for about 15 or 20 milliseconds. Sorry, 100 milliseconds, about 0.1 of a second, give or take. The gravitational wave signal that we recently detected lasted a lot longer than that, and Eric will tell you about that. But the other number that you can see here is this strain. And it has this strain amplitude has a number 10 to the minus 21, which is an incredibly small number. It's 0.00000, 21 zeros, and then a 1. And this is an incredibly small number, but it's actually very interesting. This is actually how precise our measurement has to be. And what it tells you is if I have some, here is my Lego again, if the length of my arm is some distance, then this 10 to the minus 21 is the fractional change in the length of that arm when the gravitational wave passed through. So I want to put that in a different context for you. On an earlier slide, I showed you my LIGO as a gravitational wave passed through, and it seemed to be moving up and down by approximately a centimetre, a handful of Lego blocks. And the strain that would correspond to would be around about 0.1, give or take, because the fractional change in distance of that arm is about a 1 centimetre change divided by a 10 centimetre arm length. So what does 10 to the minus 21 represent? Well, you can think of it in the following way. How long do I have to build this LIGO arm so that when a gravitational wave passed through, it changed in length by one single Lego block? The answer is not that I need to build it from Monash to the CBD, for example. The answer is not even that I have to build it from, Melbourne over to New York. It's much, 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 much bigger than that. The answer is I have to build a Lego arm 500 light years across. Remember that the distance to our sun is about 8 light minutes. The distance to our nearest star, other than the sun, is about 4 light years. And I need to build an arm such that it changes by one Lego block. I need to build that 500 light years across. Absolutely huge. Put this another way, the 4-kilometre arms of LIGO, when the gravitational wave passed through, the length of that 4-kilometre arm changed by 1/1000th the size of the nucleus of an atom. Absolutely minuscule change, and that's what we measured. Okay, so for that, clearly this is a precision measurement, and hopefully you would have heard that very, very recently, on October the 3rd of this year, 3 gentlemen were awarded the Nobel Prize, and these are the gentlemen who are credited with basically forming the LIGO experiment and the LIGO collaboration. So this is Ray Weiss on the left here, Barry Barish in the middle, and I think I'm allowed to say Monash University Monash University's Kip Thorne. Kip came and gave a public lecture out here about 2 years ago and visited the university for approximately a month. And these three were credited with winning the Nobel Prize. Unfortunately, the fourth gentleman who probably would have won the Nobel Prize as well passed away earlier this year, just before the Nobel was awarded, Ron Draver. But really, those four are really credited with coming up with the idea for the experiment and seeing it the whole way through to fruition. Of course, it's a 1,000-person strong collaboration, including a number of people here at Monash University, approximately 15 people at Monash, plus about 50 people in Australia. And we contribute in a lot of different ways. So this is where we were earlier this year. I want to now start getting into August of 2017. And August was an amazing month for us. And the first amazing thing that happened was this. So I've told you all about this detector, these two detectors that we have in the US, one in Livingston, Louisiana, and the other in Hanford, Washington. But there's actually a third detector, and this one was a little bit late coming online, and here it is. This detector is called Virgo. It's in Italy, just outside of Pisa, and instead of having 4-kilometre arms, it has 3-kilometre arms, and it's not quite as sensitive just yet as the other instruments, but they're hoping to get it that way. And through the LIGO Virgo collaboration, we actually share data and we try and do the same astrophysics. And so I'm going to take you now to the 14th of August of this year. Prior to that, what I'm showing here is a sky map of all of the gravitational wave detections that we have to date. So you can see the first one here in this dark green is known affectionately as GW 150914, which is to say we discovered, or it came through our detectors on the 14th of the 9th month, 2015. And what happens when a gravitational wave passes through your detector, or it passes through a couple of detectors, is it passes through one detector at one point, and then a fraction of a second later it hits your other detector. And you can use that time difference to say, aha, the gravitational wave must have come from somewhere over there. But that's unfortunately really the best you can do if you just have two detectors. Gravitational wave detectors don't give you direction, and so it's only by using the time difference between the time of arrival that you can try and get a handle on where a gravitational wave came from. And if you just have two detectors, then the best you can do is somewhere over there. But that's not really good enough, because what we want to do is we want to detect a gravitational wave, and instantaneously we want to send an alert to all of the telescopes around the world and say, a gravitational wave event just happened, which is to say a huge explosion happened somewhere in the sky. Can we see that using traditional astronomy techniques? And this will become very important later with what Eric's going to tell you. But of course, if you say it came from somewhere over there, and each one of the telescopes that looks has this really small field of view and struggles to see anything bigger than a tiny sort of pixel on the sky, then that's not really very helpful. So you can see here our first four detections, GW 150914, GW 151226, known as the Boxing Day event because it came on Boxing Day. LVT 151012, also a huge sky region. This isn't given a GW name because we're only about 97% confident that it was a gravitational wave and not something else, whereas the rest of them we're, for all intents and purposes, 100% confident. And then the first one of 2017, known as GW 170104. And all four of these had these huge areas on the sky where we didn't know where the gravitational wave came from. And the reason for that is we only detected them using the two detectors in Hanford and Livingston. But early August, the Virgo detector switched on. And it was actually only due to switch on for approximately a month. And so everyone had their fingers crossed, hopefully we get to see something. This would be really amazing, prove all of that hard work that the Virgo scientists have done, prove it worthwhile before the instruments got shut down for about another year for planned upgrades. And so on the 14th of August, 2017, this gravitational wave passed through. And it's absolutely amazing because what you can see is, you can see the signal in Hanford, you can see the signal that we received at Livingston, and it looks much the same. It looks beautifully the same. And what's incredible is you can see the same signal in Virgo. So we got this gravitational wave that appeared in all three of our detectors simultaneously. And because of that, and this is important for our story later on, because we got these three detectors detecting the same event, here is the sky location. You can see it's absolutely tiny. It's this very sort of pale green color. Compared to the other ones, it's absolutely tiny. So instead of telling the telescopes we can see it somewhere over there, we can now actually say, aha, it's about there, which gives the telescope some chance of actually being able to detect what we call an optical counterpart, or some kind of light, whether it be gamma rays, X-rays, optical radio, some kind of light rays coming from that same source. Now, of course, it's worth remembering all of these things that we're showing up here, these 5 different detections, are all binary black hole mergers, which is to say 2 black holes, and remember a black hole doesn't emit any light, so 2 black holes have collided, and you know what happens when something that doesn't emit any light collides with something else that doesn't emit any light? No light gets emitted. So it's all very well to tell the telescopes, go and look over there, but you're not actually expecting to see anything. And so this gets us the whole way up to August 14 of this year. A little summary, this is the stage was set. LIGO's second observing run was coming to a close. As I mentioned, Virgo was only due to stay online for approximately a month before all 3 instruments were going to be shut down. So we had collected about 117 days of simultaneous LIGO data, plus about 20 days of simultaneous LIGO plus Virgo data. We were due to be shut down on August 25, 2017. And then all of a sudden, August 17 came along. And at 10:41 p.m. Australian Eastern Standard Time, something amazing happened, which I'm going to let Eric tell you all about.
Thanks, Paul. I'll now take over and tell you how this story unfolded for me as a gravitational wave astronomer witnessing this event in Australia. And my story begins in Mount Beauty. I was traveling on my first Australian snow holiday with my kids, and I left the evening before the event that I'm going to be talking about, and went to sleep kind of early. And the next morning, my phone was buzzing. I was getting text messages. My email was completely filled up. And so I turned over my phone, and there was a text from Paul. So let's see what he said. So gravitational wave astronomers kind of speak to each other in code, and I'll try to translate this text message for you as I read it. Paul writes, I know you're on holiday, but you'll want to hear this. BNS, that means binary neutron star, with Hanford-Livingston signal-to-noise ratio of 30, coincident short gamma ray burst, an interesting high-energy neutrino that overlaps with sky location, but is 155 seconds before the trigger. This was an amazing text to receive, and what Paul was telling me was that we had discovered a binary neutron star coalescence, that there was a flash of light called a gamma ray burst that had been associated with it, and that it was all an extremely loud, very convincing signal. The other bit in this text message about there being a high-energy neutrino seemed just too astonishing to believe on top of all of the other discoveries that were implied in this text message. And indeed, the one bit of the discovery that did not withstand subsequent scrutiny was this high-energy neutrino claim. But this was an amazing moment for me. And so let's take a look at the data that was then available for us to look at that morning. What did the gravitational wave detectors show us? So here we're going to see an animation, and we're going to look at 2 time series. On the bottom is a representation of the data that LIGO took, and the horizontal axis is time, and it's going to play from left to right, and you'll see the vertical axis here is the frequency of the gravitational wave signal. and you're going to see a characteristic chirping sound. We're going to see a gravitational wave signal begin at low frequencies and then chirp up to high frequencies. Now, gravitational waves, it turns out, are interesting because they emit frequencies that are similar to the frequencies that you can hear with your own ears. And so in addition to seeing the gravitational wave signal, you'll be able to listen. And the tone that you hear, the frequency of the audio, is going to correspond to the rate at which the two neutron stars rotate around each other before they smash into each other and collide. Simultaneously, we're going to look at the upper panel. This is going to be a time series of the Gammaray observations that were observed by the Fermi satellite. This is a satellite that circles the Earth and looks for flashes of very high energy photons from outer space called gamma rays. And the gamma ray signal comes 2 seconds about after the gravitational wave signal. So you'll hear a chirping sound as the two neutron stars get closer and closer and eventually collide. And then you'll hear the sound of a short gamma ray burst being detected by a gamma ray burst satellite. So let's play this now. So that little bell associated with the gamma ray burst is, of course, a joke. But the gravitational wave signal that we heard is an actual representation of the data that we had available to us this day following 1708-17. And what's remarkable about this data is that you can see this track so easily visible to the naked eye. And in fact, GW 1708-17 was remarkable because it was the loudest gravitational wave event ever detected. It was also the first time where we had seen the collision of two neutron stars. And neutron stars are special because unlike black holes, they are capable of emitting light. And this means that it is worthwhile for our astronomy colleagues all over the world to race to point their telescopes in order to catch a glimpse of the light that was created when these two neutron stars smashed into each other. So we were able to pinpoint with the LIGO detectors a fairly small region on the sky where this gravitational wave signal may have come from. And that's indicated on this slide on the top right-hand corner. That little black line is showing you a 5 degrees piece of the sky, and the green ellipse is an indication of where LIGO was able to trace the event to. We were also able, if you look at the bottom right plot, to know where on the, how far away the object was from Earth. And we were able to deduce from the gravitational wave signal that it was 130 million light years away. So LIGO and Virgo have about 70 partner institutions from around the world who operate telescopes at various wavelengths, from radio to optical, ultraviolet. And these various groups all over the world raced to point their telescopes and start scanning this little region of the sky, hoping to be the very first group in the world to catch a glimpse of light associated with a gravitational wave detection. And inside this little patch of sky, there were many galaxies that could have been the host to this gravitational wave event. So what most of these astronomy groups did is they pointed their telescopes at each of these galaxies in turn. And one of these galaxies is NGC 4993, which is an elliptical galaxy. And one group called SWOPE, pictured here on the top right of this slide, eventually saw something remarkable. Here is an image, a pair of images showing you what SWOPE saw. On the left-hand side, we have a plot showing a reference image. This is from the Hubble Space Telescope, taken back in April of 2017. And this image is to show you what that patch of sky looked like before the gravitational wave event went off. On the right-hand side, we have an image from SWOPE, excuse me. And the SWOPE image is taken 11 hours after the two neutron stars collided. So it took this long for the alert to be sent out and for telescopes to find this event on the sky. But what they're looking for, basically, it looks like a star that was present in this image that was not there before. And this thing that looks like a star is this gravitational wave event that has created this new glow that was not previously present. And if you look what this red arrow is indicating, you can see that there's a new flash of light. And this new glow on the sky corresponds to the first ever observation of light from a gravitational wave event. So once SWOPE was able to pinpoint exactly where on the sky this binary neutron star coalescence took place, they sent out a notification to all of the astronomical partners of the LIGO and Virgo collaborations. And basically anyone in the world who had a big telescope oriented their telescope in order to catch this fading glow, which will be eventually remembered as the best studied astronomical event ever. And this is what people recorded. We're going to see now another movie, and there are two plots that we're going to watch simultaneously. On the left-hand side, this is essentially a photograph of NGC 4993. This is similar to the image we looked at on the past slide. And you're going to see the event, GW170817, appear as a blue dot just up and to the left of this kind of glowing halo. It will appear bright and blue, and then it will fade over time and turn a little bit redder. On the right-hand side, we're going to watch what's called a spectrum. And the horizontal axis here is the wavelength of the light that's emitted from this event, and the vertical axis is the brightness. And shorter wavelengths of light correspond to blue light, and longer wavelengths correspond to red light. And you're going to see the spectrum shifting from blue to red as the system evolves. And I'll narrate along as it goes. So here it is. The event appears and rapidly fades. We're now 3 days after. You can still see it, but it's turning red. 5 days, redder still. 6 days. 8. At 9 days, it's very hard to see. And by about 11 days, it's fading into the background. So what makes this light from a neutron star coalescence? Well, neutron stars are remarkable objects. A neutron star has a mass more than the mass of our sun, but compacted into an object which is only about 20 kilometers across. This means that they're extremely dense. A single teaspoon of neutron star matter weighs about 1 billion tons. And when these two objects collide, they fling off ejecta. And this ejecta is bits of radioactive matter. And there are sort of two parts to the signal that we were able to see with our astronomical colleagues. The first part is the Gammaray burst. And the Gammaray burst is created when a jet of highly energetic material is shot off from the top and bottom of the neutron star merger event, and it's funneled by magnetic fields. But additionally, there is a material kind of flung out more isotropically, more evenly. And this material is highly radioactive, and it's essentially the radioactive glow of this nuclear waste that is causing the image you saw fading from blue to red. And this glowing blue dot is called a kilonova, and we think that it is created from the glow of radioactive material that's been ejected from a neutron star coalescence. So this event lit up the electromagnetic spectrum, and it was observed by dozens of telescopes all around the world, from the radio end of the electromagnetic spectrum to infrared, optical, ultraviolet, all the way up to X-rays and gamma rays. And the different parts of the different wavelengths of light that we are able to observe tell us about different parts of the event. So for example, the gamma ray burst tells us about the magnetic fields which funneled high energy jets of particles and created these extremely energetic gamma rays. The kilonova tells us about the production of radioactive waste, which is flung outward. And the radio tells us about how this ejected material smashed into the surrounding interstellar medium and created radio waves. So what I'm going to do for you now is play a movie which sort of shows you all of these events taking place. First, you'll see the two neutron stars coalesce. This is the gravitational wave signal. Then you'll see the gamma ray burst shoot out jets. And finally, you'll see the glow of a kilonova expanding, producing this radioactive waste material. So here is the in-spiral, getting ready to merge. Gamma ray burst, kilonova, shocks in the interstellar medium. Ad for NASA. So we saw this thing all across the electromagnetic spectrum, and different wavelengths of light told us about different parts of the signal. So the kilonova, that's that radioactive junk, that we saw in optical light, light you can see with your eye, infrared, and ultraviolet. The jet we know about from the gamma ray burst, and colleagues in Australia saw radio waves from this event, and that tells us about the interaction of this gamma ray burst with its environment. So with so many different wavelengths of light and so much physics to understand, there have been a flurry of publications and talks as people, there's more science going on right now with this than we can digest, than we can read, and it will take months and years to really understand this one event. There's so much going on. All right, let's skip over that guy. So let's put these binary neutron stars into context with our binary black hole friends. This is a little picture showing you masses of different things that LIGO has observed. The blue things are black holes, and the bigger the circle is, the heavier the black hole is. The lighter blue ones are things, black holes that have been observed by LIGO, and the purple circles are black holes that we've inferred by looking at our own galaxy with X-rays and seeing some object orbiting something that doesn't emit any light and working out that it must be a black hole. So here are our black holes that we all know about, and here are neutron stars. So neutron stars are not unknown to astronomy. We've seen neutron stars using radio waves and X-rays, but we've never seen two neutron stars merged together, and these two orange ones are ours, and they created this new guy right here. And we don't know if this new thing that created is a neutron star itself or a black hole. A little bit more information about the signal. You heard earlier this 6-second chirp, but in fact the signal was present in our detectors for over a minute. So it would be quite boring, though, for us to sit here listening to boo. It's very slow building itself up to the chirp at the end. The two neutron stars cycled around each other 3,000 times before they merged in our observing band. And the strain, remember the measure of how small space-time was deformed that Paul told us about, was 10 times less than our first binary black hole detection. So this means that LIGO had to measure distances smaller than 1/10,000th the size of an atomic nucleon over a distance of 4 kilometers. One of the amazing things we were able to do with this event is measure how fast gravity moves with unprecedented precision. So general relativity and Einstein tell us that gravity is supposed to move at the speed of light. This is part of Paul's lecture, which I took notes on. But this is something, we're scientists, so we have to test this. And the idea is that if you have a flash of light from a gamma ray burst and gravitational waves, they can have a race. There they go. And they travel 130 million years before they reach us at Earth. So the dinosaurs were around when this thing merged, and it would be another 60 million years before they went extinct. When the gravitational waves finally reached us at Earth, they were still just right neck and neck with the gamma rays. And because these two things arrived at the same time and they had so long to get out of sync with each other, we know that they must have been moving at about the same speed. What else does this event tell us? It tells us that the long-held belief that bursts of gamma rays that are seen periodically, that when they're short, that these come from merging neutron stars. And there's a fascinating story behind this. So the first time that gamma ray bursts were observed was in the 1960s, but we didn't know about it until the 70s. And the reason is because the first gamma ray bursts were observed by US spy satellites that were observing Russia in order to see if they were in compliance with the Nuclear Test Ban Treaty. And to the concern of this project scientists, they periodically saw flashes of gamma rays, which could be associated with illicit tests, but were somewhat relieved to find that they were coming from space. On the other hand, I don't know, maybe the Russians are better than other things that could be coming for you, but it was eventually decided these must be coming from, we think these are coming from neutron stars smashing into each other. This was a mystery in astrophysics until we now have evidence for this link, direct evidence. Gold. I have on my hand a gold wedding ring, seemingly unconnected to gamma ray bursts, binary neutron stars, but it turns out gold is a great mystery to astrophysicists, or it was. And the reason is that it's hard to make gold. Most of the mass, the elements around us in this room, are forged in regular stars, like our sun. In order to make heavy elements like gold, you can't make them in a regular star. You need a cosmic cataclysm. You need a lot of radiation and high temperatures. And so it had been a mystery. Where does gold come from? Based on the observations of this kilonova, we now believe that there are, in the radioactive ejecta of these two neutron stars, that there was enough gold created to account for the gold observed in our solar system on Earth, and potentially the gold in your own jewelry is in fact forged in the furnace of a binary neutron star coalescence. So that's kind of cool. And here I pass off again.
Thank you, Eric. So now's the time when we sort of give credit where credit is due, and we actually have a very large team here at Monash, and so I'm going to introduce you to a whole bunch of people very, very shortly. But this is a photo that we took it was actually just in the wake of the Nobel Prize announcement, and you can see Sylvia is holding a cake there that she made. Did she make it? I'm not sure. She took credit for it. It said, "Congrats, LIGO." And this is basically our group. Unfortunately, Kendall couldn't be there that day. Year 11, looking, I'm not sure what that facial expression is, but anyway, couldn't make it that day either. But so I want to introduce you to a whole bunch of people in this group, and what we're going to do is we're going to have a little bit of a panel session for question and answer time with these other faculty members and postdocs in the group. We've also got a lot of PhD students and honours students here as well, which is actually a very exciting thing. So we've actually, in this picture, there is 4 honours students, so that's 4th year undergraduate students, and 1 3rd year undergraduate student as well, who actually had opportunities to be working directly with LIGO data and working actually on this experiment at the time of this amazing discovery. And so this is, just some of the opportunities that we're able to provide here at Monash. So I will mention a few different things that we've done. This whole team played a huge role in this entire sort of discovery process. We've made some significant contributions to the actual discovery paper, plus about 5 of the companion papers as well, including co-authoring a number of them and directly working on some of the physics and some of the science for a number of them as well. So that's sort of a broad picture. First I want to introduce Xingjiang Zhu, who's going to hopefully come down here. So this is Xingjiang, everyone. Come on down. I feel like, what's that show? Come on down. No. So Xingjiang is a postdoc who recently arrived just earlier this year as part of the OzGrav Centre of Excellence for Gravitational Wave Discovery. Has played a huge role in all of this. He's trying to understand some new ideas about how these neutron stars, when they, just prior to their merger, what they're doing in terms of their spin and in terms of some of the physics that we understand from the galactic population of neutron stars and how that combines to these observations that we're making extragalactic as well. So have a seat, we'll do questions shortly. So Letizia Samet is going to come down next. You guys haven't sat in very clever spots at all. Should we go out of order? So Letizia is a postdoc who's been here for a number of years now. She's been actually leads one of the data analysis working groups within LIGO. It's called the Stochastic Background Working Group. And so she co-wrote one of the companion papers as well. Fantastic, thank you very much. Kendall Ackley has a star next to her name. So Kendall can come down as well. A round of applause for Kendall. So Kendall had an amazing task. Kendall turned up probably on about the 16th of August, arrived from Florida to start a new postdoc here. All of a sudden, this binary neutron star goes off the next day, and Kendall is tasked with coordinating practically all of Australian telescope follow-up effort. And sort of coordinating all of these telescopes, all of the people working on the telescopes. Many people didn't agree with the science that they should be doing and how this should all fit into place, but they managed to produce an absolutely amazing paper that includes all of the facilities, the Australian facilities on them together, and this is an amazing paper and a beautiful team effort that was really led by Kendall on sort of her first day on the job, which was, I think, a little bit of hard work. So well done, congratulations on that, Kendall. It's been a bit of a baptism of fire there. So then next I'm going to introduce Rory Smith. So Rory has, sorry, yes, we should clap for Rory as well. So Rory has just been, there's some seats over this side. We want you to sit on a different side. I don't know. Rory has just arrived recently. You can take it over there. Has just arrived recently. You're going to leave Duncan on his own now. Rory's just arrived very recently from Caltech as well, joining as part of OzGrav also. Rory has done some amazing work in this rapid parameter estimation, which sounds like, you know, just 3 completely jargony rubbish words to most people here probably, and to me as well. But what this basically means is when we detect a gravitational wave event and it comes through our band, and what we want to actually be able to say is, I have this gravitational wave signal, and now I need to understand what caused that signal. Was it 2 black holes with a mass of 30 solar masses, or was it 2 neutron stars, or was it a neutron star, a black hole? What was it? What were they doing? Were they spinning? What was their orientation? There's all of these really sort of finicky details that we really need to understand to be able to understand any physics at all. And Rory's team over in Caltech in particular developed this way of doing this that was about 1 million times faster than what people were doing previously. Am I overselling this? About 1,000. Yeah, okay. We'll go somewhere in between, 100,000. About 1,000 times faster. But what this basically means is now it only takes us about a week to do this. Whereas, you know, if you multiply that by 1,000, it takes you 1,000. It used to take us 1,000 weeks to do it, which basically means you wouldn't be seeing these results. We'd be keeping this a secret from Michael for another 10 years or so, rather than getting out all of these papers in 8 or 9 weeks. So that's, you know, absolutely amazing contribution by Rory and his team, and we're incredibly lucky to have him on staff here as well. Looking forward, this is hopefully a picture that you can sort of see. This is a telescope that's being built in La Palma in Tenerife, and it's called the GOTO telescope, and it's being built as part of a Monash-Warwick alliance. And Duncan Galloway is somewhere in the room. Here he is. Come on down. Do you want to sit on that side too?
I'll sit on my own.
Okay. So Duncan is building this telescope. Unfortunately, it wasn't quite ready, but it's going to be capturing all of these amazing neutron star mergers in the next observing run. So all right, so I guess now it's time to open the floor up to any questions that people might.
First, we can thank Eric and Paul for a great talk.
Hello, I've got a question for Duncan. What are we looking at here?
So what we can see here is this is a telescope that's designed to look for these transients. Now, what we normally find with LIGO transients is, they have very poor localizations of these sky areas, these enormous fields. And so what we normally think that, or what we predicted that we need to do would be to cover these regions very quickly in case this transient is fading very rapidly. So what we optimise for is we have actually 8 separate telescopes there, all on the same arm, and each of these has a field of view which you could put the moon there, if you could think of the size of the full moon on the night sky, about 16 times. Is that right? Yeah, I think so. No, actually, what's 8 by 8? Yeah, that's 64 times. So in terms of astronomical instruments, they have an enormous area, and that was purely to get this to be able to image very quickly these enormous fields. And so that's the design that we set up there. At the moment, we only have 4 instruments, and we've got 4 more coming, but we'll have that full-scale operation hopefully early next year.
Letizia, what about dark energy? Do you want me to do it?
Yeah, I think Paul is actually excellent.
I'm not. So the reason I prompted that question, a great question as well. The reason I prompted that question is because this is actually, we managed to, using these observations, actually start to do cosmology. And so while at the moment we can't say anything about the full evolution of the universe as a whole, we hope to be able to do so very soon. So what this is basically to do cosmology. Hopefully many of you will remember Brian Schmidt won a Nobel Prize, the great Australian Brian Schmidt with a very similar sounding accent to Eric. Won a Nobel Prize a number of years ago for discovering the fact that when we look at supernova, distant supernova, they appear to be going away from us faster than we expected. And this is due to the accelerated expansion of the universe. So we know that the universe is expanding, but it seems to be accelerating even faster and faster and faster. And this is due to this dark energy thing. And so what Eric has just brought up here is a plot from one of the papers that LIGO produced, where we're actually starting to do this kind of cosmology with gravitational waves as well. We're not quite as good with precision yet as the supernova folk. And the reason simply is that we detected one of these things so far, and they've got a whole bunch of supernova. But it's a completely independent way of doing it. And so we should be able to really be competitive doing cosmology in that sense in the next few years.
So we don't actually see, you don't see any emission line or anything for the gold, but we have models like this one, and this is like a fancy astrophysicist periodic table. And as you have this is the little green and yellow thing is those are heavier elements getting made, and as you go up and toward the right, they're getting heavier and heavier. And as this movie plays, you're making you're watching a kilonova, a model of a kilonova, and the elements are walking up the periodic table, and you're starting with heavy elements, and they irradiate each other and create heavier stuff, which then eventually decays into this black line, which is stable elements. I'll leave this here.
So we have a question from the young gentleman down here. I'm gonna relay this. Do gravitational waves carry mass? Which is an amazing question.
I think one thing we know is gravitational wave carries energy. So energy is equivalent to mass, I think that is yes.
Yeah, so for this, and this one had 3/100ths of a solar mass of energy was 3. So you take 3% of the sun, just convert it into pure energy, E equals mc squared. That's how much energy was carried away in gravitational waves.
These ideas of multiverses come from some higher dimensional theories. This observation and the fact that the speed of light and the speed of gravitational waves is very similar actually rules out a lot of those theories, or at least does a lot of damage to them. So there's, it can start to impact on that field.
The black hole measure has a distinct sound to it, and obviously the binary stars have a distinct sound to them as well. Is there any difference between those sounds? And what other sounds did you want to look for in the future?
Every gravitational wave has its own sound, and binary black holes are short. The heavier they are, the shorter they are, and the lower they are. So if you want to do an impersonation, a binary black hole that's really heavy makes a whump sound because the waves are longer, so it goes whoomp, but it's short. Binary neutron stars, because the masses are lighter, then that means the signal lasts for longer, and the final pitch is higher. So this is this chirping sound we have that you heard at the beginning. In addition to these long chirps and the short whumps, you can look for bursts. This is like if a supernova went off in our own galaxy, you listen to the gravitational wave sound from it, it would be like, it's just a really short, it's a messy sound too. It doesn't have a tone associated with it because it's not one thing going around another thing very regularly. It's just matter flying every which way. So it has like an ugly, scratchy sound. Letizia and Rory are both working on finding a hum. So they want to find the gravitational waves that are going off, the neutron stars, for example, that are merging every 15 seconds. And if you listen to that, that would just be like a staticky, like television, like if anyone is old enough to like remember when televisions used to have static, but it's like shh. And that we haven't seen that yet, but we think that's always present. And as our detectors improve and as our algorithms improve, we are going to try to dig out that static noise. And maybe we can take one or maybe two more questions.
So we have a question from our second youngest audience member.
How far can LIGO see in light years?
Great question.
In one sense, it depends how bright the gravitational waves are, how intense they are. Right? If we had a very, very bright thing, you could see it a lot further away than would be a much dimmer thing. Okay? So at the moment, we think we can see these kind of neutron stars that are crashing in together. I think out to about a distance that we talk about, what we say 60 million parsecs. Okay, and that's about 200 million light years. Have I got the conversion right?
That's 3.
2 or 300 million, 100 million light years. And so that's a distance that would take light 200 or 300 million years to travel over. Okay, so it's an enormous distance. But of course, there's a lot more universe out even beyond that distance. Okay.
I think one final question.
Yep.
Since light is a transverse wave, is gravitational wave a transverse or a longitudinal wave?
So this is showing gravitational waves coming through the board, and this is showing two of the polarizations. This is showing just one of the polarizations of gravitational waves. We sometimes call it the plus polarization, and it's another polarization of the stretches.